Hello, everyone. I'm Angelo Corsaro, Zetascale CEO and CTO, and welcome to our webinar series. Today, we're going to discuss Zenoh, as quite often during this webinar. And more importantly, we will go through the first part of a three-episode mini-series that will be addressing Zenoh and several of its advanced concepts. So we'll wait a couple of minutes to give time to people to join, and then we'll get started because there is quite a bit of material to be covered. Whether you are joining through LinkedIn or YouTube or Twitter, don't hesitate to ask questions. We'll be answering those as they come, if we can, or else at the tail of the presentation. Okay, so I'll go ahead and start sharing my screen. So you should be able to see my title slide momentarily. And this is going to be a rather interesting webinar because there will be plenty of demonstrations. Unmuted? Mirrored? Yes. Okay, thank you. Okay, there will be plenty of demonstrations and some new tools that it's still in development phase, but you'll be able to try as a preview. So let's share the screen. So you should be able to see my screen, and let's hang over another 1 minute, and then we'll get going at 3:03. So as always, I'm here in Paris. For those of you that like weather statistics, it's a beautiful day. It has been a beautiful week, and it looks like it will be sunny for the rest of the week, which is quite nice. Okay, ready to go? Fasten the seatbelt, and let's go. Okay, we need to start with some resources. During this webinar, we'll be using a new tool that I've been crafting precisely for the webinar. This is a tool that in the team we wanted to have for quite some times, but we always had something else to do. And for this webinar series, I said, well, we really have to have this tool because it will make it so much simpler for people to really touch with their hands the Zenoh primitives and perhaps more easily experiment with how the publish subscribe works, how query work, the query targets, and all the things that we have discussed in previous webinar, and I will go into much more details in this webinar. So you will be able, alongside with me, to use this tool, and perhaps even after the webinar, you can check out the repository, build it, and run it. But in general, through this tool, you can scout around, as we will see. You can publish, you can subscribe, you can do query, you can do queryable, you can define storages, which is very handy because in order to start experimenting with storages, all of a sudden you don't need to understand the Zenoh configuration, which, by the way, we'll cover not today, but I believe either in episode 3 or episode 2. I will show you how to run the tool, but before getting there, there is already an extensive documentation. But if you want to be able to build the tool, you will have to just clone the repository. So right now the tool is available on a fork out of my GitHub account. Check out the dev Zenoh Swiss Army Knife. This is the code name from this tool branch. Then get into the Zenoh directory, build, if you want to build release, but more importantly, build feature with stats feature. Why build with this feature? Because I will be showing you some information concerning data traveling across perhaps a Zenoh network. If you want to have those kind of information, if you have one of our tools, and if you're using our tools even with the open source version, you need to enable stats. Then obviously our commercial edition have more stats, but even in the open source, you have some basic stats that you can enable with this feature. And then in your target release, you will have Zenoh, and with the -H or -help option, you'll start to navigate. But again, we'll extensively go through the tool. Now, let's go back quickly to setting the context. So today, there are two topics that are relatively hot, or very hot, I shall say. One is robotics. And if we make a parallel with the body, robotics is really about, the structure, the human body, the structural elements, right? And, obviously there is computer science everywhere, but, a big part of the robotics is the mechanical engineering, as it is for our body in a way. Then everyone is obviously talking about AI for various reasons. But again, if we continue this parallel with the human body, then AI represents the brain, right? And in fact, I would say the brains that we have in our body. Because for those of you that are passionate about our nature, it ends up we actually have two brains. The bigger is here, but there is a brain as big as the brain of the dog in our belly, and apparently that used to be bigger than the one we had above our head, because before the discovery of fire and cook food, digestion was taking lots of intellect, let's say, and so you have as many neurons in your belly as much as you have in your brains, and these two brains are connected. Anyway, I mean, this is not a course on neurosciences, so let's remain on this path for the time being. But again, we have the body, we have the brain, but sometimes we forget about something else that is as important, right? And it's the nervous system. So if we can function as we do today, if I can grab things, throw them away, and grab it again, it's because I have obviously, the physical part. I can move my hands, my robotics. I have my brain, but I have, a proper nervous system. And without a good nervous system, there wouldn't be any catching in time, right? This would be falling on the ground. And so if we are now trying to build systems that have intelligence, interact with the physical world, we better have an incredible nervous system. And this is the goal that we had set in a way to solve when we invented Zenoh. Not just at the scale of a robot, but at the scale of a cloud to microcontroller system, as we have explained in the past. And so the focus of Zeta scale in general is really about communication, and you can make the parallel with nervous system and building nervous system that will support contemporary systems that again impose massive challenges over us because of their scale, both geographical scale, because of their heterogeneity, and because of their increasing need to interact with the real world. And the real world doesn't wait, right? Okay, so going a little bit deeper into the problem that we face. So the problem that we face is that it's not just about building a robot again that can catch this on the fly, right, and making sure that everything works together. But we have to have system that usually have multiple robots and a human operator and other device that need to coordinate with each other. And so it's not just a problem, of dealing with the microcontroller, the microprocessors within a device. There is the problem of communicating between devices in a fleet. There is the problem of communicating with operators or other intelligent elements or storages or whatever that span into this continuum that goes, again, from a microcontroller up to a data center, right? And when trying to build this kind of system, so far, we were struggling. And this is a struggle that has been there in robotics, is there in automotive, it's there in IoT and edge, is there in aerospace and defense. It is, in fact, a very cross-industry challenge. And when building this kind of system, usually people were resorting to some kind of, stitching together a different technology and hoping that actually the result in my view, it's like a digital Frankenstein, right? Would kind of work. But this is, error prone. It's tedious, it's not efficient. And again, I mean, it isn't how we should be building systems, right? And again, this is not how we are built, because the incredible beauty of our complexity stems from orthogonality and simple composable primitives that make up us as they make up the universe in a way, right? And so we try to do the same, and we try to say, okay, so what are the primitives, right, that we would need in order to have a solution that would allow us to deal with building this system that span from the microcontroller up to the data center and addressing the distributed computing problem. Because distributed computing is not just about shuffling data around, right? This data has to be stored and eventually retrieved. And actually, I also have computation that needs to be coordinated, need to be triggered, and so on and so forth. That was the problem that we wanted to solve. And the solution that we came up with is Zenoh. So Zenoh is the first protocol of its kind. Zenoh is a pub/sub query protocol. And hopefully at the end of this webinar, it will be clear why pub/sub query. And the nice things of having pub/sub and distributed query abstraction is that through this simple yet and orthogonal abstraction, we can unify data in motion, so distribution of data, data at rest, which means distributed queries, and distributed computation from the microcontroller up to the data center. The last webinar we did was on Zenoh Pico. So if you want to see the kind of microcontroller we can run on, just check out our latest webinar. Now, the other nice things about Zenoh is that Zenoh provides you with location transparent abstractions. Why is that important? So if you've used pub/sub in the past, you know that since the introduction of the information bus and subject-based communication, or publish subscribe, that brought location transparency in the sense that if I'm interested in receiving some data, I do not need to know where the source of the data is. I just need to declare my interest with respect of the data that I want to receive. And different systems provide different way of declaring the interest. In Zenoh, use key expression, right? In MQTT, use subject, and so on and so forth. But again, I say the what. I declare what I'm interested in. I name the data as opposed to pinpointing a place where the data should be coming from. And that's fundamental because the ability of introducing and leveraging location transparency and the ability of relying on technology that are location transparent for data dissemination makes sure that it's much easier to do, for instance, fault tolerance. Okay. Now, how about data at rest? If you think about databases and how databases work, when I issue a query on a regular database, I need to know where the database is running. Okay, so I need to issue a query on that database or on that database. So databases are location aware. And what Zenoh does, as we will see, is that introduces this concept of queryable that are oracle around the network that declare that they are able to answer query. And then it's Zenoh, depending on the data you're looking for, that decides where to route your query, as we will see extensively in this webinar. And finally, the same is true for computation. All of a sudden, if you name the data that you are interested on, right, and that might trigger a computation, all of a sudden, where the computation is doesn't matter anymore. And again, I will show example to make this a little bit more concrete, because I know that when I say it this way, it sounds very abstract, and we will be very hands-on, and we'll leverage Zenoh AI to actually touch it with our hand. The other important things is that Zenoh has built-in support for shared memory and zero copy, as well as built-in support for distributed storage alignment. And I will also cover that today. Why is zero copy important? Well, let me show you, right? So first demo. What we have done recently, for those of you that know the Z capture and Z display application that we have in Zenoh demo, where we have extended this to use our shared memory, okay? And so what I will do here, I will start Z capture, but actually let me show you the command line So there are various things. You can choose the mode. So if you want it to be a peer or a client, and again, we'll discuss this in more detail coming up. But you can choose the resolution, you can choose the delay, you can choose if traffic has to be best effort, you can choose the congestion, and you can choose the image quality, okay? So default is 18, which means pretty poor. So let's do something that produces, that capture an high resolution. So let's do resolution minus R, and let's do something like HD MI 9020 times 1080. Then let's say image quality. Let's say, for instance, 80. Yeah, I mean this would be pretty good in terms of quality, but of course the size of the data will be fairly big. We're talking about several megabytes of per JPEG, and then as a period, a sampling period for the camera. So let's do minus D. Let's do something like 20 frames per second, 50 frames per second. So I've started here my capture. Let's do the display. So here you see I'm displaying. And so the question now is, how much bandwidth am I using on my laptop? So let's check it out, okay? So I've ordered this by in alphabetical order. So here we have Z display and Z capture. And what you will notice is that, in fact, the received bytes, it's like ridiculously low, okay? But yet you see that, the image is coming. How is it coming? Through shared memory, obviously, right? Because this image has an incredible high resolution, and you see that the impact on data is nothing, because it's not even receiving around 9 kilobytes, 7 kilobytes of data per second, which is just metadata. Okay, so how can you do this with Zenoh? And again, I want, in fact, to tease you throughout the entire webinar, right? Introduce concept, look at the demo, look at the code, and then go back and make sure that we keep this very hands-on. So how do you do that with Zenoh? How hard is it? Let's look at the code. So what I've done, and I will do this in several instances as we go through the webinar, I will use breakpoint, not just to debug it, right, but to highlight the area of the code that are interesting, okay? So if we go a little bit up, we see that this is the capture application, okay? And we see that here, I'm actually creating a POSIX share memory provider backend. I've explained this in the past, but again, we'll go into the ins and the outs of share memory next webinar. Today we'll use it, we'll enjoy its benefit, we'll see how to use it, but won't explain the internals, okay? We'll get more details next webinar. So, but I mean, why do we need a backend? Because in Zenoh, you can plug multiple backend. So by default, we support POSIX, but if you have an NVIDIA, and we have some users, some customers that have written Zenoh share memory provider backend for NVIDIA or for some Qualcomm hardware, then I can go and allocate memory from there. And once I have a backend, which in this case, it's indeed a backend for POSIX, then I can create a shared memory provider, right, in which is backed by this given backend. And once I have this, right, allocating memory, it's pretty straightforward, because I have my provider and I will allocate with the given shared memory size. Notice that in this case, the shared memory size is the length of the buffer that I'm getting from OpenCV, okay, after the encoding, so after this line. And in this case, I'm aligning the length to 8-byte boundaries. This is something that actually will change probably in the future, but as of today, you have to provide length that are aligned with the alignment required that you have defined for your provider, okay? Now, notice also that in this case, I'm allocating with a policy that says, please block on the fragmentation and garbage collection, okay? So as we will see, right, we do well, you can do, the allocation can fail if there is no more memory, and then you can trigger allocation as a consequence of this failure, or you can ask, please, to garbage collect and eventually defragment if needed to do so. Now, this is one option. Another option, and that's a perfectly legal way of building your application, is that you have a periodic task that triggers the garbage collection, okay? What is the advantage? Is that I can amortize the cost of garbage collection in that case. Here, I'm garbage collecting at once I fail allocating, and potentially I might even need to defragment. You might wonder, in this specific application, why on earth I need to defragment? Well, if you actually make a test and look at the size produced by the codec, well, actually, the image size is not always the same. And it's kind of logical, right? Because it depends on the quantity of the information that there is on the image. If there was, a background without anything else, that can be compressed massively. But if it's a very rich framework with lots of different colors, lots of different shapes, then obviously, there is more information, and because of Shannon, obviously the size will be bigger. So what is happening every time I'm allocating here is that I'm allocating a buffer of a different size. And so what Zenoh will do is that it will garbage collect, right? So detect whatever it's free. And then if needed, it will coalesce all the buffer into adjacent buffer in bigger buffer, so that you will be able to use those, okay? And then when you do, how do you write a shared memory buffer? Well, it's no different than writing any other data. That's completely transparent. Now, notice that unfortunately, because of the current, let's say, OpenCV API, we can't loan this buffer that we are allocating in shared memory to OpenCV in order to actually already encode and write in this buffer, okay? Would have been nice, but there isn't an option like to do that. That's unfortunate. And so we have to have a copy, but it's a local copy, and then on the wire, only some little meta information will go. So how about the reading side? Well, on the reading side, I'm receiving a sample, and that's it. I mean, I have a sample. I don't even need to know that's shared memory. Okay, I'm transforming into an OpenCV vector of U8, decoding it and displaying it. So pretty straightforward, easy to use, and you saw the impact on the network. Imagine sending images that are 8 megabyte to, if you want to build a processing pipeline without using zero copy and shared memory. That would have used lots of your memory bandwidth, which is not good. Okay, so let's go back to our slides. And again, storage alignment I'll demonstrate later on. So Zenoh was written in Rust for security, safety, and performance. We have language binding for plenty of programming languages, but I will be mostly using Rust and some Python, but today will be mostly Rust. Again, built-in support for shared memory, as we saw. And the other important thing is that Zenoh was designed to run at a data link. And in fact, a Zenoh runtime can use multiple links at the same time. So the same application can use TCP/IP, quick serial, and a Unix socket to talk to different applications, and can route also across those. And it's actually available on embedded devices, and the wire overhead is extremely constrained. So I'll skip this slide. Now, there is just to clarify something. Zenoh actually refers to two things. Refers to the protocol, so the abstract concept of the protocol, and actually the Rust implementation of the Zenoh protocol also happens to be called Zenoh. And then we have another implementation of the Zenoh protocol written in Rust that we call Zenoh Pico, okay? And this targets microcontroller. It is fully interoperable. It is the Zenoh protocol, okay? So it's not another protocol like, in the case of MQTT, MQTT-SN. Well, the only things that they have in common is the name, because the protocols are different. Same things with DDS. You have DDS and DDS XRC. It's like a joke, because those are two completely different protocols that need to be bridged. Here, it's exactly the same protocol, exactly the same primitives, but one is implemented in C. Why? Well, because Rust, it's great for embedded system, but the environment for embedded still is dominated by C and C++. The other nice feature that we have is that you write a C++ application for Zenoh. At compile time, you can decide whether you want to target the Rust or the C part. Okay, in terms of supported OS, anything where Rust runs, we have also ported, and that is part of our commercial offering, Zenoh to QNX, and all the depending packages, and we maintain those for QNX. And then for embedded targets, it's a plethora of those. And if there is anything we don't support, you can port it and contribute it, or let us know. Usually, it's pretty straightforward. Okay, so Zenoh can run in any topology. We can do peer-to-peer. We can do mesh. Okay. And a Zenoh application can decide also the role that it wants to take. We will see that with the Zenoh AI, right? But you can decide to be a peer or to be a client. And if you're a client, that means you are kind of lazy in the sense that you will use something else that is available on the network in order to route the data that is relevant for you or that you are producing to the interested parties across the network. In Zenoh, we also have this concept of routers that obviously can be used to mediate communication between clients, but in general can be used to establish an infrastructure that spans across the internet. Now, what is the difference between a router and a peer? Well, conceptually, very little, right? Because as we will see, both of them can have plugins. But the real difference is that the default behavior is slightly different, right? The default routing algorithm is different, and they, by default, they already introduce different routing domains, which helps with scalability. And I think the way in which you should think about routers is that those are infrastructural elements that you use to scale and to give you a way of control boundaries, okay? So for instance, for those of you that have seen our webinar on ROS2, will know that with Kilted Caillou and the ZenRMW, every robot will have a router. Why do every robot has a router? Because that completely decouples the communication between the Zenoh peers and the different ROS nodes that are inside the robot and the external world that is very different. Because the external world, you might want to downsample, you might want to secure your communication, you might want to control what goes out, you might want to change the reliability or the congestion control for given information. And so that also, the router also gives you a very, very nice way of doing all of that. And in general, think of it as a way of composing and scaling, okay? And an element that is more infrastructural than application-oriented. Now, if we put all of this together, I just want you to realize that application, right, not only can communicate over mesh, but every link of this mesh or click or whatever that is can be a different kind of link. So for instance, here I have this peer that communicates through serial with a client. And actually, this would be the case of this application, where we have Zenoh Pico running on the open OCR and regular Zenoh running here and communicating through serial, the serial link. Okay, so Zenoh over serial. And then the application running here would be using, again, serial to communicate with this, and perhaps QUIC or TCP/IP to communicate with the rest of the world. And so these are the sort of things that you can do. And if you compare this with any other protocol, right, this is so flexible and so important for these kind of systems, right? So you understand how the protocol was really designed to support you in highly heterogeneous system, and again, to really run in this environment that span from the microcontroller land, where you might need to deal with serial, with Bluetooth, with OpenThread, and so on and so forth, up to the data center, where perhaps you might want to use QUIC, for instance, okay? Okay, so if you put topology in perspective, this is how Zenoh compares to MQTT and DDS. So essentially, Zenoh doesn't pose any constraint on the topology. MQTT forces you into a client to broker, and DDS forces you into a click-based peer-to-peer, where every peer has to know every other peer. And that's one of the source of the scalability issues of DDS2. Other important things that we will see in action is the plugin architecture, right? In Zenoh, you can have plugin for third-party protocol. So we have plugin for MQTT, plugin for DDS, and so on and so forth, and plugin for databases. This database become essentially backend that our storage manager can use to store data, okay? I mentioned before that Zenoh provides storage alignment. The storage alignment is independent of the actual backend. So if I have Zenoh storages that needs to be aligned, I can align a storage that is backed by main memory, another that is in Amazon S3, another that is based on a RocksDB, and that still works, okay? Again, we will see storage alignment in action today. I will explain the details, the algorithm, because it's pretty neat next webinar, because we won't have the time to cover everything in one webinar, but we'll introduce the behavior and then look under the cover as we go through. Okay, so you know what? Let me show you some storage alignment, just as a small teaser. And so we start, we keep this running with multiple demos. So I want to go here. And what I'm going to do, if you want to start a storage with Zenoh, so I've copied actually the Zenoh I here, okay? So if you want to start a storage and you don't know, well, first of all, let me go a little bit slower. You see that here, you see all the commands that are accepted, okay? So I can start the storage as such. So let me start the storage. And if I want to understand how to use a storage, I can do bin Zenoh I storage. Yeah, I forgot the I. Operator error. Yeah, this tells you that the storage essentially expect potentially some option and a key expression. And the options are complete, align, and help. Okay. So in this case, let's assume that they say that, and I'll explain what complete means. I want a storage that it's complete, that aligns, and let's do it under demo /*. And on the command line, I need to put quotes here. So these are as declared the storage. Actually, let me do something else because it will be nice. So if you notice on the Zenoh I options, right, I can ask to enable REST and I can ask to enable the admin space. So let me show you other example of the cool stuff we can do with Zenoh. Because what if you try to define a storage and it seems like this storage isn't working? Was the storage, is the storage reader? How can you check it out? So let me show you. So we say REST and let's put it on the port 888 and then admin. Okay, now if I open a browser and I go on localhost 8888 / you see that actually I'm tapping into what we call the administration space. Again, we'll cover it, but for the time being, okay, you can see that there is here, right, a storage that is using memory as the backend, and the key expression is demo.**. Okay, so what I'm going to do now, I'm going to do some publications. Okay, so let's do Zenoh. Whoops. Publish. Let's say demo A. Let's say 1. Okay, done. Was this stored? Well, I'm anticipating, but I will go kind of anticipating something with the demo and then explaining the concept. And as I said, we'll keep this slightly different than usual. Okay, a little bit more hands-on. So I will do Zenoh I want to query demo, /*, for instance. Well, actually, indeed, So I got, there is one key currently that is demo A, and the value is 1. And here is the timestamp, okay? Now, let me put, let me do another put to, obviously, if I issue another query, right, then I will get 2 values, no surprise. Now, what I'm going to do, I'm going to start another storage, okay? With the same key space, so it will be a replica in that sense, right? Storage demo / star. And now, you know what I'm going to do? I'm actually going to kill this storage here. So this storage is gone. And hopefully, I mean, I didn't kill it too fast before they aligned the storage, but we'll discover it after the query. Let's do a query, and boom, I still get the data. So what happened? Well, the storage got aligned, okay? And that's pretty cool. That's part of the demo of storage alignment, but our storage alignment is even cooler because this is a simple example, right? The storage is starting up, it aligns, but what if the network partitions? We'll come back to this in a moment, okay? So let's go back to the slides. And let's start talking about programming abstraction. So Zenoh is built upon 2 primitives that operate on named data. One is pubsub, that the other is query reply, okay? And named data is represented by a key and a value. For instance, bot1 sensor speed 25. These 2 primitives are orthogonal, and they are implemented very efficiently in Zenoh. And essentially, those are all you need to build the distributed systems, where you usually need to deal with, moving data around, querying data, so storing and eventually querying data, and dealing with computations, okay? So what you see here, and this will become clearer with some other demo, is that I'm showing the logical flow of information, right? So when I do a publication, logically, the information flows to all subscriber. How that flows, well, it depends. And it depends, as we'll see from the topology. Zenoh takes care of that. Likewise, when I do a query, in terms of API, the operation is called get in Zenoh, then the query will be routed to querybles, and I will receive a stream of results. Sorry? Okay. So they let me know that the window is a little bit too small. I guess the shell, I will expand it when going through the examples. So in this case, the Zenoh routes the query to the queryable, and then eventually the queryable provides a series of answers and informs when there are no more answers. Okay, again, a queryable provides typically a finite stream of answer. You could have some weird queryable that actually never provide, never end in a way. That's also possible, and there are some creative use of that. But again, in this case, usually, you do a query, the query is routed where it makes sense, and then you get a finite stream of answer from the collection of querybles that have been triggered. We will see how this is used in practice, okay? Now, just to make it a little bit more, to give some example, here you have 2 publishers, one that is publishing for the key bot1 sensor speed, the other one for the key bot2 sensor speed. And here you see some example of subscription with key expression that would match this publication. Okay, again, pretty straightforward. And the only things to notice is that the double star matches an arbitrary number of chunk, where a chunk is nothing than an array of bytes separated between 2 slashes. Okay, so that's pretty straightforward. So you can actually compose these 2 abstractions, pubsub and query reply, to do obviously pubsub, big news, to represent remote computation, because in the end, a queryable represents nothing but the generalized form of computation, because it can transparently deal with replication and partitioning. And we will see that again in action. And again, this is and mobility. Once you realize this, you really realize the power of Zenoh. And I hope that today I'll manage to visualize it for you. with some nice demos. And then storages are nothing but the combination of a queryable and a subscriber. Okay, so let's go back to the example that I showed you, and I'll make sure to increase a little bit the size of the font of all my windows. Whoops. So hopefully this one is a little bit more readable. I'll increase them all. So Tim, please let me know if, So if we start again, oh, actually it's still running here. So let's do another publication. Let's do C3. So what happens here, I'm doing a publication, but as there is a storage whose key expression matches the key that I'm publishing, this publication will reach the storage, because again, a storage is the combination of a subscriber. You have to think the subscriber as the writing half of the storage, and a queryable. Because when I do then a query, right, in this case, I'm querying demo star, okay? So, and I get ABC, but I could query A and only get A, okay? Obviously. I don't know where the storage is, okay? It's up to Zenoh to realize. And the same would be true for the computation. So, and in fact, let's play something interesting, okay? Let's do the following. Let's create now, because we can also create transparency between computation and storages. So in this case, the storage is not complete. Okay, so what I'm going to do, I'm going to define a queryable, a very simple queryable in this case, because we will see that then with this application, you can even use Python script to provide the behavior of the queryable. But in this case, will be a very simple queryable that does the following. So queryable, and then the key. So let's say demo /*, and it responds, okay, because this is the reply. Well, in fact, we respond with hello, I am a queryable. Okay, so if I do now a query, in fact, I get to answer. Okay, for this key, I get hello, I'm a queryable. Okay, and that's quite interesting. So all of a sudden, you don't need to know, and you can change while developing your system if something is computed or is looked up in a database. But the way in which you get information is completely transparent. Okay, let's go back to slide. So yes, I actually covered this. This just visualize what just mentioned, that a storage is the combination of a subscriber and a queryable. Then you have a backend that actually stores the data. And again, in Zenoh, we don't want to invent databases. I mean, there are lots of very smart people that have worked on optimizing databases for decades. We leverage those, and we actually unify them behind an abstraction. And so all of a sudden, even your query doesn't care what kind of database you have behind. Okay, it could be influx, could be a file system, could be memory, and so on and so forth. Okay, so let's go a little bit deeper. We've already played with query reply, and there are some details that we need to understand. So I mentioned before the term complete. I don't know if I said anything about target, but let's go a little bit deeper. So when issuing a query, Zenoh will route it to a set of queryable. But a set of queryable that will be addressed depends on two things, in fact. It depends on the query target, which can be best matching all or all complete. And then it also depends on if the queryable are complete or not. Okay, what does it mean for a queryable not to be complete? And you know what? I want to jump forward. I had told you that this was going to be exciting. A good way of visualizing a queryable as complete or not complete a queryable that is complete promises that essentially he has, if a value exists for a given key, he has it, okay? And a queryable is not complete in the case in which it tells, well, I might not have all values. Why this? Okay, so is it just to make your life harder? No, because as you know, we want to simplify our life and your life. The point is that imagine that I have, let's say, storages, and I don't, for some reason, I don't want the storages to be aligned by Zenoh. Okay, I can suffer partitioning. The storage can come and go. And so when I issue a query, actually, how do I know what is the right set of these storages, potentially with overlapping key expression that I need to address? If they're not complete, I cannot tell. So any storage that intersects with my query will have to be asked because it's not complete. And the way in which storage A is not complete or queryable A is not complete might be different on how queryable B is not complete. So in that case, right, if they are non-complete, I need to hit them both, okay? And so if we go back now to the queryable, suppose that here, I'm issuing a query to compute a navigation path, okay? So if I use as a target all, then this query will be distributed to everyone. They will do their computation and send back the result. If I do best match, right, in this case, it will hit the complete and the incomplete. And if I do the all complete, it will only hit the two complete, okay? And we will see some more example. So how can I use queryable? So suppose that in fact, I have a queryable on a given robot that allows me to retrieve status, okay? How do I get this status? Again, the status might be written on a file. Imagine the Linux proc file pseudo file system. It could be accessed by specific hardware registers. It could be computed. I mean, there are multiple ways. And all of this can be shielded behind a beautiful queryable. So in this case, what I want to do is to get the battery status for bot 1. So notice that as the queryable, they are declared as the bot ID /status/star. When I do get bot status 1 battery with best match, it will hit that robot and will give me, as a response, the one value, 84%, plus the kind of string terminator that tells me I have nothing else to tell you, okay? The query is done. Now, if I want to retrieve battery status from all of them, then I can do get bot $. That's the efficient way of wildcarding within a chunk. And in this case, they will all receive the query and will reply me in some order with their battery, okay? Plus the nil terminator that says, the query is over. Now, what if I want to know the robot that have a battery level that is lower than 0.5? In Zenoh, you have support for predicates. Okay, so a key expression, a query expression is a key expression. In fact, a selector, that's actually how it should be called. A selector is the composition of a key expression and a predicate. The predicate is after the question mark. We support some predicate, built-in predicate, but you can do your own predicate because it's up to the queryable to interpret what happens after the question mark. So in this case, I want to get the status for the robot that have a battery level that is less than 50%. I issue this query, right? All of them receive it. And obviously, the queryable one tells me, I have nothing to tell you, right? So I get just the fact that, he received the query, but has nothing to reply. So I get what I call nil for simplicity here. And the other two reply me with their actual battery status. So hopefully you're starting to see how powerful these queryable are. And you also understand maybe why I get upset when people compare the queryable to RPC. I mean, RPC, first of all, is not name-centric, right? And it's about the client and the server. The server dies, I can't call anything anymore. And that's one-to-one. This is really a principle of query reply. Okay, so we have a queryable, you have a querier, and it's about triggering distributed query that can then, in a specific case, collapse to the special case of an RPC. But that's far more general and far more powerful. Okay, what time is it? We have 10 more minutes. You know what? I'm gonna just real quickly go through some slide here, and we'll go to do some other demo. So in Rust, the API is pretty straightforward. You can use synchronous or asynchronous API. If you want to use the sync, recall to include Zenoh trait. Okay, you don't need to publishers in Zenoh to produce data, right? The put operation is the act of publishing some data for a key, and you can do it once you have a session. You pass the key, you pass the value. You can define a publisher. A publisher is really an optimization, and I'll discuss the optimization that are done in the next webinar, the optimization that are done under the hood. And by the way, we discussed some of those in a webinar that I did with Olivier 2 webinars ago, okay? Subscription are pretty straightforward. You declare a subscriber, you provide the key expression, and you get a stream that you can iterate through. If you use asynchronous programming or synchronous programming, because you have stream also for the synchronous programming case, as if it was a container. And for those of you that are fond of functional programming, then you can use also, obviously, higher order programming in any programming language that supports that on stream, like Rust. Whoops. What happened here? Sorry, there was a bug on my slides. I'm not sure what happened here. Let me jump. I think I erroneously hit some Control-C, Control-V while I was on the shell, but I was selecting this. So let me jump on query. So we have seen query in action. I've explained queryable. This is how you declare a queryable. You declare a queryable. You can declare if it's complete or not, and you pass a key expression. And again, completeness, we will see it in action in a moment. And this is how you do a target. You pass the target, the consolidation, and we'll see consolidation in action in a moment, okay? Okay, so let's go back and let's play a little bit more. So what I want to do now, I want to have 2 storages. Yeah, let me start 2 storages that are non-complete. Okay, so we do this one and we'll do another one here, exactly the same, okay? So we have 2 storages. Let's do a couple of put or publications. Let's say A1, B2, and that's enough. And now I'm gonna make a query for demo star. I got lots of value, right? So by the way, notice that Zenoh tells you, look, consolidation mode is not defined. So I took by default none, so I'm not consolidating. And notice that I'm receiving one first reply for demo A, demo C, and demo B, and then some other replies. And those are the reply coming from the 2 storages. Why? Well, there are 2 things happening here. First of all, the default target is best matching, okay? But as those storage are not complete, well, I mean, I don't know if they have the complete set of keys, right? In this case, for instance, they are not aligning. So if there was some partition, they aren't. So I would have to tap on both. And so that's what Zenoh does. And then as by default, the consolidation is nothing, that means that I'm receiving all the sample and Zenoh is not discarding duplicate and providing me the latest value. So I can fix that. So if we look at the query, let's look at the query options. So in terms of option, I can pass a file as an attachment. Okay, we will see that when that comes handy. I can specify a kind of target, so it could be best, all, or complete. A consolidation could be known, monotonic, or latest, and well, then the help. So if I now change to say, look, I want you please to consolidate the data and give me only the latest. In this case, you see that we only get the samples with the highest timestamp. Well, in this case, obviously, as there were no bad things happening, right? No partitions, no whatever. The timestamps for the value that are in the two storage are exactly the same. But in a large distributed system, right, there could be updates still propagating. And what this ensures is that when you start consolidating, is that the consolidation happens as soon as possible and only keeps propagating the latest value. So depending on your use case, right, if you're querying, perhaps storages, usually you want to consolidate using either the monotonic or the latest, okay? For computation is slightly different, okay? So let's play now with, before getting to computation, let's play a little bit with completeness and let's see what changes. So let's define the storage to be complete. I believe it's complete. Yeah, it's complete, the option. So let me copy this up here. So I hope you appreciate how convenient is this command line to experiment now with Zenoh. And now let's do, in this case, the query without consolidation. Oh, in this case, I'm getting samples only one. Why? Well, because I've said that the storage are complete. So if they are complete, I can pick one or the other. And so which one would Zenoh pick? Good question. Let's investigate this. So let's stop this. And what we're going to do, I need another shell here. I'm going to start a large graph of Zenoh routers, okay? So I think I should have it, I should have the command here. So what this does, and we have shown this with Olivier in the past, this starts a graph of 14 nodes, which I'm going to visualize using the Zenoh C2, the Zeta C2. Okay, so this is actually, let me increase a little bit this one. This is the graph, and this is the tool that I've started, okay? Now, the nice thing is that if I hover on top of one of the nodes, I will see the locator, okay? So what I'm going to do now, instead of using storages, I'm going to use queryable, okay? So I'm going to declare a queryable let me check the, oops. Okay, so, and I want to show a couple of things at the same time. So I want the queryable to be complete, okay? So I will hit only one. I want to use a script. Or maybe, well, actually, not yet. I'll show you the script afterwards. And then let's do again for demo. No, you know what? I'm going to compute. Okay, let's do this way. Let's do the demo /*. And here I'm replaying I am. A. And in fact, you know what? I'll do something else. I'll name this application queryable QA, like this, okay? Okay, oof, I didn't make any mistake on the command line. And what well, actually, no, I forgot something else. What I want to do also, I want to specify the endpoint. So bin, let's look at some help. So I can actually specify the endpoints and disable, well, in fact, I will set it as a mode client, okay? And I will specify the endpoint. And I will tell you in a moment, I will show you in a moment, well, we will choose together. So I will do mode client, and then as an endpoint, we'll do the following. So TCP / and then I don't know the port, we'll choose it together in a way. Okay, so this is our graph. You know what? I'm going to put one of the queryable here. So the port will be, or we'll ask it to open a session here, will be 9008. And by the way, here you see my IP address, but this is also reachable through, they are all running on my machine, so will also be reachable through the loopback interface. So I said the port was 9008, yes. Okay, so if I did, yeah, there we go. So already discovered, there it is. Okay, so now we have a queryable that it's here, right? And I'm going to put another queryable here, and this is 9003. So what I'm gonna do, I'm gonna do this, whoops. So I think it was, yeah, let's put it on the 9003. Okay, good. And let's see if it does appear. Yeah, it's there. Great. And in fact, you know what? Let me just do like this so that the network map will be bigger. Whoop, and you will be able to see it nicely. Well, I did a mistake because I needed to change the name of the application. So let's change the name of this application. This is QB, and I want unqueryable B. Okay. So queryable B is there, queryable A is here. Okay. Now what I'm gonna do, so let's look at this. This is 9. What I'm gonna do, I'm gonna issue a query. So in this case, also as a client, let's say, and I'll explain in a moment why. Well, because as a client, they have only one session, okay? And so I can ensure that will connect to nothing else, okay? So it has to then be routed to something else. Because if I connect it as a peer, what could happen is that the client, well, if they were all peer, they could discover each other and get connected potentially, okay? But this way I avoid connection that I don't want to have. So mode client and then endpoints, I believe it was 12. So we said this one, oh, it was 9 actually. 9. Okay, so before I execute the query, what do we have? We have two queryable that are complete, are for the same key, okay? I'm making a query on a given key expression, and my client, my application will be a client that establishes a session here and does a query. Which queryable do you think will hit? Well, actually, both of them are good, but in the case of Zenoh, right, Zenoh will hit the queryable that is the closest. So will be QA. Let's verify. Oh, down here. Yeah, okay, so good. And let's suppose that I'm moving and perhaps I'm here, okay? So here I should hit the queryable B, okay, because here we got the queryable A. So if I'm in here, so I try with the 9001, that would be the same one where we have the tool connected. And in fact, I get queryable B. So why does this matter? Well, this is important because, first of all, it allows you to have information that, first of all, can be contextual. If you want to have anything that is contextual with respect to your location, like weather, I don't need to say weather Paris. I tell, please give me the weather. And depending on where I am, right, there is someone in the lab that is connecting to my tool. Depending on where I am, right, you will get the right information. If you have applications that have mobility, I mean, this is completely transparent because Zenoh supports session migration. And all of a sudden, as I migrate, right, I always hit the right queryable. And more importantly, you know, suppose even from fault tolerance perspective, from a fault tolerance perspective, what can happen? Oh, there are some guys. Yeah. What can happen from a fault tolerance perspective? Suppose that now I partition the network. Okay. If I partition the network, then I can still access those. Or let's say that I kill QA. Okay. So let's stop QA. And I do a query still from 9008. I still get the data, but I get it from queryable B. So I have to travel more. And now if this one comes back, okay, and I issue the query, boom, I get it from queryable A, which is great, right? Okay, so we are 6 minutes past the hour. There were a few more things that I wanted to show, but I guess I will have to reserve those to the next. Well, no, I will show you one more thing, okay? So that you can do with this tool. So here we had a queryable. Now I could do something like this. Payload. And here I can say script. Script. So actually, this is a Python script. And you can do a Python script that operates on payload and key expression. So actually, let me close this for a moment. And if I now do something like this and I pass a body, reverse this string. Oops, I had not started the queryable, so no surprise I didn't get any answer. So queryable started. Oh, I wrote something stupid apparently. Well, I would say never mind. I mean, we'll investigate this next time. Let's jump back to the slides because it's already quite late. And we have far more things to cover for next time. Okay, so in summary, Zenoh is one of a kind of a protocol. It unifies data in motion, data at rest, and computation, and is the only protocol that is really able to run from the microcontroller up to the data center and cover essentially all the functionality that you need to build distributed system, right? With good abstraction, without any constraints, and extremely easy to use. So what I suggest, check out Zenoh. If you want to contribute other feature, please do. I'm considering also to integrate, because many people ask us, can I do video streaming on Zenoh? We always say, yeah, you can. But we might integrate Z capture and Z display also in Zenoh. And perhaps as a feature, okay, so that it doesn't require dependency on OpenCV. And I think at this point, we're going to address questions. So let me stop sharing my screen so that I can look at the questions. Okay, so there is a question concerning the use of shared memory and whether it is enabled by default. Well, shared memory isn't enabled by default. So how do you enable it? Let me show you real quick. If we go again, for instance, here on the ZCAM, if we look at the cargo TOML, when you build Zenoh, you need to enable unstable and share memory. Okay. Now, there is another question concerning plugins. Okay. How does it works? Well, I mean, using plugin in Zenoh, per se, it's straightforward, right? If you look at the code of Zenoh, it doesn't do anything special to use plugin other than essentially crafting a configuration. So if you look at the file, crafting a configuration, for instance, when it declares the storage, well, it crafts a configuration before that enables plugins, and then it uses the admin space, as we will see, in order to dynamically create a storage, okay? But the real tricky part when dealing with plugins is actually Rust and the fact that there is no API stability. So if you want to use your own plugins, no problems. But if you want to use Zenoh plugins, so if you, as I showed, you want to have an application that loads, a REST plugin or a storage plugin, then you better use the same cargo lock as Zenoh, because otherwise you'll get into Rust issues with API compatibility. Okay. I guess that's it in terms of question. At least I don't see any other questions. At this point, what I would like to do is to thank everyone for joining us today. I look forward seeing you in 2 weeks. Well, we'll dig still deeper on Zenoh. And meanwhile, have fun, enjoy the new tool, and let us know what you think. Take care. Bye.